Welcome to the Depth Dive. We've got a really interesting source today. You sent us, it's a book called Royan Shingpo that translates roughly to True Beginner Crawling Electricity. And that's kind of our mission here. Unpack the big ideas from this book, especially if you've ever found things like, well, electricity and magnetism a bit daunting. I mean, just think about it. Electricity is everywhere, right?
Um,
Powering your phone, your lights, everything. And magnetism, it's sticking notes to your fridge, guiding a compass. For ages, these two forces just seemed completely separate, like totally unrelated. But what if they're actually, well, two sides of the very same coin? So our deep dive today is all about that journey, uncovering how we figured out this deep connection. We're doing it, true beginner style. Understanding this really makes so much modern tech just click.
That's absolutely right. And we're aiming for those real aha moments for you today. Because grasping this link between electricity and magnetism, it's not just some old science story. It's genuinely the secret behind, well, almost everything techie in our modern world. Power grids, microchips, you name it. By the end of this, you'll probably start seeing things a bit differently.
Okay, so let's dive into this journey. And it really starts with something like a happy accident almost. Before the early 1800s, scientists knew about static electricity, that shock from the carpet, and they knew about magnets, obviously, how they attract iron and stuff, but they saw
hmm
absolutely zero connection. None at all. They were just filed in totally separate mental boxes. Then along comes Hans Christian Ørsted, a Danish physicist. And he stumbles onto something almost by chance that changes everything. So picture this. Ørsted's giving a lecture, doing some demonstrations with electricity. He's got a wire, a battery, a strong current flowing. And just nearby, maybe sitting on the demonstration table, there's a compass. Just a standard compass.
Right. And then something completely unexpected happens. As that electric current starts flowing through the wire, the compass needle, it moves. It deflects away from north.
Wow, just like that.
Just like that. And this was, well, revolutionary. It was the first solid proof that an electric current actually creates a magnetic field around it. Nobody had seen that direct link before. And Ørsted, being a good scientist, he didn't stop there. He tried reversing the current in the wire, and the
Hey.
needle moved again. But this time, it swung the other way.
So definitely not random.
Exactly. It showed a clear cause and effect. Current flows one way, magnetic field points like this. Current flows the other way, field points like that. This simple observation really proved electricity generates magnetism. It was the birth of electromagnetism as like a unified concept, a huge shift.
Yeah, you can imagine the buzz that must have created. Once Ørsted showed this dynamic link, it just flung open the doors for physics research, didn't it?
Absolutely. A whole wave of brilliant people started digging into it.
Mm.
You had Biot-Savart, Lenz, Arago, Weber, all adding pieces.
Right, a real gold rush of inquiry, like you said. But sticking with our true beginner theme from the book, let's focus on the next big steps. Ørsted showed that it happens. But how do you actually describe this invisible force? How do you know its direction? Who figured that out?
Okay, that's where André-Marie Ampère, a French physicist, made a huge contribution. He built right on Ørsted's discovery, wanting to quantify it, figure out the direction of this new magnetic field, because, it's invisible. How do you even picture it?
Right.
Ampere came up with a really clever and honestly quite intuitive way to do it. It's often called the right-hand rule. Maybe you learned it in school.
Vaguely rings a bell. How does it work again?
Okay, so imagine you grab the wire with your right hand. Your thumb points in the direction the electric current is flowing. Then your fingers, as they curl naturally around the wire, they show the direction of the magnetic field lines. They form circles around the wire.
Okay. So, thumb for current, fingers for the magnetic field direction. Simple.
Exactly. And that's why it's so brilliant, especially for the beginner's level we're talking about. It took this abstract, invisible force and gave people a simple, physical way to visualize it, to predict it.
Makes sense.
It really helped make the abstract concrete. You could suddenly see the orientation. It's a perfect example of crawling electricity making a complex idea graspable.
Okay, so Ørsted, electricity makes magnetism. Ampere. Here's how to figure out its direction using your right hand. That's already a huge leap. But then comes the really big question, doesn't it?
The flip side.
Exactly. If electricity can create magnetism, can magnetism create electricity? That sounds like the next logical, but maybe even harder question. Who tackled that? You mentioned Michael Faraday earlier.
Yes, Michael Faraday, an incredible English scientist, largely self-taught, which is amazing in itself. He became obsessed with this reverse idea in the early 1800s. If Aristotle's effect works one way, why not the other? So he started experimenting
Right.
tirelessly,
Hmm.
moving magnets near wires, moving wires past magnets, trying everything to get a current to flow just from magnetism.
And it wasn't easy, I gather.
No, not at all.
Yeah.
For a long time, he got nothing. You can imagine the frustration. Maybe it was impossible, but he kept at it. And eventually, through sheer persistence, he found it. He discovered what we now call electromagnetic induction.
Electromagnetic induction.
And this is where it gets really, really interesting. This is a key light bulb moment for you listening. The core idea, keeping it beginner-friendly, is this. It's not just having a magnetic field near a wire that makes electricity. If you just set a magnet next to a wire and leave it there, nothing happens.
Okay.
The absolute key, the crucial part, is that the magnetic field around the wire has to be changing.
Ah, there it is again. Changing. Not just existing, but changing.
Precisely. It has to be getting stronger or weaker, or maybe the wire is moving through the magnetic field. Any kind of change in the magnetic environment around that wire, that is what induces an electric current to flow in the wire.
So the change is the trigger.
That's the magic word, change. Without change, no induced current, no electricity from magnetism. This discovery was monumental. It unlocked the secret to generating continuous electrical power. Just imagine Faraday in his lab finally seeing that needle jump on his meter, not from a battery, but just by moving a magnet. It must have been breathtaking.
Okay, so that discovery, electromagnetic induction, sounds incredibly important, but let's bring it home. What does this actually mean for us today? Why should you, listening right now, care about a changing magnetic field?
Well, here's the really mind-blowing part. This principle, it's how almost all the electricity you use is generated.
Almost all of it. Think about power plants, hydroelectric dams, coal plants, nuclear reactors, even those huge wind turbines.
They're all based on this.
Fundamentally, yes. The only big exception is solar power, which uses photovoltaic cells, a totally different process converting light directly.
Right.
But nearly every other large-scale generator uses electromagnetic induction. They have big coils of wire, powerful magnets.
And they spin them. Right. Exactly. They use turbines spun by water, steam, or wind to create relative motion. That rotation is what causes the changing magnetic field. As the magnetic field lines sweep across the wires or the wires cut through the field lines, that change induces the electric current.
And that's the electricity flowing out to the grid to our homes.
That's it. It's everyday magic, really, powered by Faraday's discovery.
Wow. Okay, so generators, that's huge. Are there other, maybe smaller scale examples?
Oh, absolutely. Once you get this core idea, changing magnetic field induces current. You see it in lots of places. Think about your contactless payment card or maybe your transit pass.
When you tap it.
Yeah, when you tap it on the reader, there's no direct electrical plug, right?
No.
The reader emits a rapidly changing magnetic field. Your card has a tiny coil antenna inside. That changing field induces a small current in the card's coil.
And that powers the chip.
Exactly. Just enough power for the chip to wake up and communicate with the reader. Wireless power transfer right there.
Okay, that makes sense. What about wireless phone charging? Same idea.
Same fundamental principle. Your charging pad creates a changing magnetic field. Your phone has a receiver coil built in. When you place the phone on the pad, that changing field passes through the phone's coil and induces a current, which then charges your battery. No wires needed between the pad and the phone.
So cool.
It really is. Technologies that might seem like, well, magic, suddenly become understandable when you grasp this simple concept. Change is key. Changing magnetic fields make electricity flow. It's one of those foundational ideas that just clicks.
What an amazing arc. We started with electricity and magnetism seeming totally separate. Then Arsted sees a compass needle twitch. Boom, electricity creates magnetism. Ampere gives us the right-hand rule to figure out its direction. Then Faraday, after loads of effort, proves the reverse. A changing magnetic field creates electricity.
Electromagnetic induction.
Right. And suddenly, that unlocks everything from giant power plants to tapping your transit card or charging your phone wirelessly. Two forces deeply, fundamentally intertwined, shaping our entire technological world.
It really does show how powerful just asking what if can be, doesn't it?
Yeah.
And how these seemingly simple observations can lead to world-changing understanding. This whole journey eventually paved the way for James Clerk Maxwell, who took all these ideas, Orsted's, Ampere's, Faraday's, and unified them mathematically into one beautiful theory of electromagnetism. It showed that light itself is actually an electromagnetic wave. But that's maybe a deep dive for another day.
Definitely.
But the point is, understanding this connection, this dance between electricity and magnetism, it changes how you see things. So maybe the final thought for you listening is, now that you know about this hidden connection, What other invisible forces or links might be shaping our reality? What other everyday magic is out there waiting for us to connect the dots? What happens if we keep looking for those unexpected connections like Ørsted did?
That's a great question to leave folks with. Keep that curiosity going. Keep asking, how does that really work? The
Ah.
world's full of fascinating stuff like this. Keep digging, keep doing your own deep dives. Thanks for joining us, and we'll catch you on the next one.